So last week we saw those steps about naming of organic compounds. We did that last week. Let's remind ourselves again those steps because we need them. So first we identify the parent chain of carbons, that is the longest chain. This is the longest, has to be the longest chain of carbons. Then we check whether there are any functional groups, like the hydroxyl group, for example. If any, it's not necessary to have a functional group. Then we check if there are any double or multiple other double or triple bonds between carbons. And eventually, once we have roughly the picture of what's going on, then we number the carbons, starting from the carbon which is closest to the functional group, if any. Like in this case, for example, where we have a functional group, carbon number 1 would be this one, which is closest to the functional group. And then after numbering, we identify any branches. What is a branch? For example, this compound here does not have branches, but if we look at this compound here, and if we take this is the longest, the parent chain, then we see there is a branch here. So this is a branch. Something that, in other words, that is there in the place of some hydrogen, that would be a branch. Like we did the names of this one and of that one. Look at this. I remember we took, this was the longest chain, because no matter how we count the carbons, the longest number that we can find is 3 + 2, 5. It was a pentane. And here we have this branch and this branch and this branch, 3 branches here. So we need to spot the branches finally. So let us practice some more here. We did this the other last week, but we're going to talk about them when we talk about isomers. Now let's try with some of these problems to name these compounds, although in most of them the names are given, but it doesn't matter. Let's see if we agree with those names. I want to, let's start from this one here. We have this compound, it's given to us in its displayed formula. And the first thing is to identify the longest carbon chain to become our parent chain. So if we go from left to right, we have 1, 2, 3 carbons. If we go zigzag, we have 1, 2, 3. So no matter how we go, the biggest chain of carbons is 3. So let's follow this to be our chain, like 1, 2, 3 carbons. And we see that we have 1 bromine here, and also we have a methyl group there. These are like branches. They are branching. Our chain branches, in other words, but no other functional group. So these 3 carbons, this chain is will be the root of our name. And what is 3 carbons? It will be. Would you like to Oh, I don't know, something happened and things disappeared. Yeah, okay, let's try again. All right. I hope this thing records here. Okay. All right, guys. So we were here. We said that our longest carbon chain is 3 carbons, which means it's from the root will be from propane. So propane, it's propane. no double bonds, no other functional groups. But now we have to accommodate in the name all these substituents like the bromine and the methyl group here. And now, so bromine will be both of these branches will come in front of the name. The bromine will be written as bromo something, and this will be is the methyl group. It will be written as methyl something. But we also need to explain in which carbons these are located. So let's number the carbons, 1, 2, 3. Doesn't matter if we start from left or right because this is symmetric here. And we see now, write it clearly. Now, which do I write first, the bromine or the methyl group? It goes alphabetically now. First in the alphabet is B before the M, so bromo will come first. And this is in carbon number 2, 2 bromo. There, of course, I didn't leave much space. 2 bromo. And the methyl, then is the methyl, which is also number 2, but because, sorry, methyl. 2-bromo methyl propane, because this methyl cannot be anywhere else. It could not be at carbon number 1 or carbon 3, because then it wouldn't be a methyl group. It can only be in the carbon in the middle. There is no need to put a number there for its position, because its position can only be this in the middle carbon. So, but this cannot be said about the bromo. So that is why the name of this compound is 2-bromo methyl propane. Guys, do you have any questions on that? Send comments if you have if we need to explain something better. So there is the name of this compound, which is also written up there, 2-bromo methyl propane. Okay, I can make some space. Let's find another one with lots of things that lots of substituents to apply the rule that we have to show them in alphabetical order. I want something with 2, okay, let's try something from here. Let's try this one. Okay, we have the name already, but it doesn't matter. Let us see if we can get end up with the same name. All right, so we have this compound with 3 carbons in a row, but the longest chain. So it's also a type. The root is propane. Here it is propane. Now we have to add. There's nothing else here except for these chlorine atoms, one here and one there. All right, so we can number the carbons, and it is, again, it doesn't matter if we start from left to right or from right to left, because the molecule seems symmetric, so the name would be the same. So let's say this is carbon 1 and this is carbon 3. So we see that we have 2 of these chlorine atoms, and the name of these chlorine substituents goes as chloro. Chloro in front of the name, chloro, and the name then the root of the name continues. And here we have to say where they are. And also, because there are 2 of them, we must not forget to add di in front of chloro. Dichloro, because, and it's very easy to forget a di, because there are 2 of these chloro atoms, these substituents on the chain. So dichloro, and here, before the di, we need to add the numbers of the carbons where they are, and they are carbon 1 and 3. 1, 3 dichloropropane. So that is why we have this name, 1,3-dichloropropane. So there is no complication here, but the only thing that we can forget very easily is to add the di in front of the chloro, because we have 2 of these chlorines. And if we had the 3rd chlorine somewhere, say here we had, instead of hydrogen, we had the chlorine, another chlorine atom here. Instead of di, because we have now 1, 2, 3 chlorines, we should have tri. Tri stands for 3. Eh? So this would be trichloropropane. And the positions is 1, 2, 3. 1, 2, 3, because at each carbon there is one of these substituents, chlorine substituents. So here the tri is placed before the chloro, and the remaining root of the compound. How about this one? This one does not, they don't give us a name here. Let's see. Again, we have 2 bromine atoms, so we have to say dibromo. But first, what is the root of this compound? How many carbons do we have? We have 4. This is the longest chain of 4 carbons. So it's from the family of the butane. So the end will be butane, and here we're going to place the bromo, these 2 bromos here. And we must remember to add the dibromo. Uh-oh, usually run out of space. Dibromo. Yeah. This is when you write backward. Dibromobutane, and here we have to add the names of the carbons where we find these bromine atoms. And let's start numbering the carbons: 1, 2, 3, 4. So the one is at carbon number 2, and the other is at carbon number 4. So it's 2,4 dibromobutane, the name of this compound. Okay. There is a little one, the root is the methane, it's from the methane molecule. And you see we have 3 chlorine atoms attached to this carbon. That is why it's trichloromethane, because this one single carbon, it's the root is methane, for methane. But 3 hydrogens have been replaced with these chlorine atoms, and that is why it's trichloro. And there's no need to say here 1, 1, 1, because there's only 1 carbon. They cannot be anywhere else, so it's well specified. So you see, when there are small chains, like 1 or 2 carbons, sometimes even 3, there is not always need to add some of these numberings of where things are in the chain, because if there's no, if one group, one branch can only be on 1 carbon, then there's no need to put its number there, because there's no alternative. Let's try this last one. This that has fluorine and chlorine atoms. All the hydrogen atoms here have been replaced by fluorine and 1 chlorine atom. So the root here is, the chain is made out of 2 carbons here. So this is from the ethane family. So the ending must be ethane, the root. And here we have to add all the rest. And we have fluoro and chloro. Let's we have chloro and fluoro, and with fluor. Now, which one comes first in alphabetically? The C is before the F, so the chloro will go first in the name. And let's say this is carbon 1 and carbon 2. So the chloro is at carbon number 1. 1 chloro. And the fluorines now, and we have 1, how many? 1, 2, 3, 4, 5. 5 fluorines, 5 of them. So 5, remember, it comes from the number penta. So pentafluoro, that must be pentafluoro for all the 5 fluorines. So, and now look at this. Because it's only 2 carbons here, we could start numbering from 1, from left to right or from right to left. It wouldn't make much difference, isn't it? So pentafluoroethane. We could say actually 1,2 penta, don't know where to, pentafluoroethane. Such a big name for such a small compound. So this would This could be the name of this compound, 1-chloro 1,2 pentafluoroethane. Okay. Now, let us look at some examples where, look at these 4 examples. All these 4 compounds are different compounds, as you can see. Not very different, but they are different. And all are given by this. They have the same molecular formula, all of them, all the 4 of them. 4 carbons, 9 hydrogens, and 1 bromine atom, all of them. But look at how they are arranged. In the top 2, the bromine is at different positions, but the actual chain of carbon is just a straight chain. Just the bromine is at different locations, different positions. And what did I want to say here? So these 2 are 2 isomers of with the same molecular formula, in which the position of the bromine has changed. So these 2 are called positional isomers. Positional isomers. Now, since we are there, let us number them. They already give us the numbering of the carbons. So in this first compound on the left, the bromine is at carbon number 1. So it's 1 bromobutane because there are 4 carbons. The root is butane and the bromine is in the first carbon, 1 bromobutane. Here, the bromine has been attached to carbon number 2. So in this case, it's 2 bromobutane. So just the position has changed. Now, if we go to the compounds which are at the bottom now, again, these 2 compounds have the same molecular formula as the previous compounds. Again, we have 1 bromine. Here is the bromine on this one, and here's the other one. But what is the difference here? Is that the 4 carbons are not in a straight line anymore. One of the carbons with its hydrogens has come as a branch in the middle carbon in both of those cases. So I hope you can see the difference between the top and the bottom compounds. They all have the same number of carbons and hydrogens and bromine, but here we have one of the carbons with its hydrogens has become a branch to the chain, a side branch. So these are also isomers. Both of them are isomers, and they are also isomers of all the 4 of them are isomers. How can we call this type of isomerism that we see here at the bottom examples? It's because the chain has branched now. It's not a straight chain with the carbons one after the other. One has become a branch, and this is called like a chain isomerism. Chain isomerism. So let me see something in your book. It has a couple of types of isomerism in your book. It has the chain isomerism where simply one or more of the carbons of a straight chain have moved to different positions, and they have made the chain to become branched. So this branching, it's also a type of isomerism. We can call it chain isomerism. And if we were to test the chemical properties and the physical properties of these types of isomers, they could have quite similar properties, but some of the properties like the melting and boiling points might be a bit different, because you see, a longer chain, you see the top chains are longer now than the bottom chains that have been branched. So if you look at the top chains now, if you imagine lots of these compounds next to one another forming a liquid in a liquid phase, you see, because the chains are longer, the chains coming next to one another, they interact and they attract as well one another with some weak intermolecular forces between the molecules of this sort. And you see, say that you imagine another chain like this of the same type of molecule with 4 carbons in a row. All the others will be hydrogens. I'm not going to draw the hydrogens. If they come close to one another, you see that the two chains interact, they attract one another, because there are always electric forces that exist between molecules. And because the chains are longer, the longer the chains they are, the more they attract. It's like spaghetti, like sticky spaghetti. They attract one another. But if some of the carbons branch, and you see, like in this bottom example, the chain becomes shorter now, and the shorter chains interact with less, the forces between shorter chains are smaller as well. And that is why a liquid made out of this type of molecules will reach its melting point or boiling point sooner. It's easier, in other words, to break the bonds between the intermolecular bonds, I mean, between molecules in these shorter chains than break the bonds between the longer chains. So longer chains of carbons have higher melting and boiling points. I hope it makes sense. I mean, it makes quite a lot of sense. Obviously, here there are smaller forces, weaker forces between the shorter chains. So this type of differences we are going to observe in the properties, but nevertheless, they are not the same type of molecule. They're similar but different molecules. So anyway, these are isomers. So we see a case of positional isomerism in the top two, and here we see also a chain isomerism between top and bottom, chain isomerism. They are chain isomers of, if we go from top to bottom. But remember, all of them have, which is very important, they have the same molecular formula. All right. By the way, how can we name these two compounds at the bottom? Although we have their names here, they're given. Remember, we have a branch. Now, the longest chain has only 3 carbons, so it's from the root will be propane. 3 carbons is propane. But now we have to add all the extras, like the branches and the bromine atom here. So in this case, we have a bromine, which will be expressed as bromo something, and this is a methyl group. So alphabetically, which one comes first, bromo or methyl? Obviously, it's the bromo. B is before the M. So first we'll go the bromo, and it's at carbon number 1. So this is 1 bromo, and then the methyl group, which is at position number 2, 2 methyl propane. So that is why we have here the name 1 bromo 2 methyl propane, and here the difference is in the position of the bromine atom here. So the bromine atom, instead of 1, yeah, it's at position 2. So the only difference will be this number here. That will be 2 here. 2 bromo, 2 methyl propane. Okay. Do we understand the naming of compounds? Guys, please send me a message. Yeah? Okay. Nice. Let's discuss these isomers. Oh, here they are again. That's a good point to discuss in this page. Meanwhile, if you want to write a message, just write it. When we have, look at these compounds that we have on this page, they have something common. They have a double bond between two carbons. So they are from the family of the alkenes. So the root names will be from the alkenes, will end in "in." These are all alkenes. Now, when we have alkenes, a useful way to show an alkene is to have the two carbons with a double bond in this configuration. We have the two carbons, and here at this two extra bonds per carbon, we are going to write whatever else is connected to these two carbons. So in this first compound, it so happens just nothing special, nothing. The other two are hydrogens, but sometimes, like here, we have more complex connections to the two carbons. Now, look at this, for example. You see one of these two bonds that I have drawn here, the one is connected to this hydrogen, the other one is connected to a methyl group. This is a methyl group, isn't it? We can also show it like that if we don't want to make long drawings. And in this, in the other carbon here, the other carbon is connected. One of these bonds is connected, is linking a hydrogen like this one here. And the other one, the other bond, is connected to another methyl group, another thing of this type, isn't it? Now, if we see it in this way, it's easier to see if we have any isomers or how to draw another isomer of this type. So, for example, you see the way we have shown this molecule here. These methyl groups is one on top and the other is at the bottom. But we could also have another isomer of the same molecule with the same molecular formula, where both those methyl groups would be at the bottom, like if we had the two carbons here, and this can stay as it is on the left-hand side, but on the right-hand side, we could inverse those two. For example, the hydrogen could go on top, and at the bottom, we could have the methyl group. Here, you see that. So now this molecule is an isomer of this molecule, where the two methyls on the same, below the two carbons, below the double bond, whereas here it's one above and one below. And we can see that those two are also isomers. I don't think that this is not, oh, come on. I'm trying to see if they have such an example in your book. Nevertheless, this way, I hope you can see that these two are isomers of a molecule with the same molecular formula. And actually, these two cases are shown here. I hope you can see that this molecule and this molecule are actually these two isomers that I have drawn up there. So the moral of the story is that if we write the two carbons with a double bond, bonded with a double bond together, and then we can show what else is connected to each carbon, and it's easier to identify isomers of different sorts, depending on what is on top and what is at the bottom. All right, so now we need to stop here. That's enough with isomers. I hope you understand what isomers are roughly, and I hope you get the general idea of how to name compounds, organic compounds. So next week we can start talking about various reactions that different homologous groups can undergo. Okay.